when you're screen sharing. Okay, recording is started. So when you open up Solidworks, you should see this, but paying attention to the slides, you can see this assembly here. This is our injector, or our Mule 1 injector spacer. Mule 1 is our student research and developed hybrid engine. And this is a spacer for its injector, if you may have guessed. And so we'll start with SolidWorks layout. So where all of your tools are, how to access said tools, how to use those tools, go through the UVR CAD standards. So our units of measurement, how we name our parts. And then we'll actually get into the part creation, the selecting of commercial off-the-shelf parts, and then putting everything together into an assembly. So moving to slide 3 here, we are going to start a new part. So if you have this Welcome SolidWorks home screen, you can just click New Part right here, or in the top left corner, you can go File, New Part as well. And so we should get a blank canvas here. We won't be jumping right into everything just yet. I want to let you guys, or kind of show you guys what the lay of the land looks like. So on slide 4, you can see we have the sketch tab up at the top. And so that is found here, just the second one from the left. And that is where all of your sketch tools are. Your sketch is where every part starts from. And so that's going to be 2D lines on a plane. And so, and then in the bottom right is the units. So, and we'll get into how to change those to that custom you see there on the slides in just a second. To the left of the sketch tab is the features tab. And those features are, we use those features on sketches or on different like 3D bodies to edit or add things to our model. In the evaluate tab, this has a lot of, or just to the right, so past markup, there's a lot of good tools like measure or mass properties, which is grayed out since we don't have anything there. And then, yeah, those are the kind of the most important ones in evaluate. And then in SolidWorks add-ins, you can see we have a bunch of different add-ins here. And the most important one, which we will be using in the SolidWorks FEA Skilldev, which will be next week, that is SolidWorks simulation. And so if you just click the tab or click this button here, it should pop up as a new tab. But again, we won't be worrying about that until next week. You'll see the assembly. There's an assembly tab down at the bottom there, and that assembly tab. Oh, sorry, missed the part configurations. Part configurations is just over here to the right of the feature manager. And that is, or we use that, or you can make different configurations of a part. We don't dive into that too much or at all in this Skilldev. However, it is a very useful tool if you have a lot of parts that are similar but have like slight configurations for a potentially like the same use case. And then finally at the bottom there, the assembly. The assembly is not here on our tabs right now because we aren't in an assembly, but you'll see it when we open up our first assembly document. Does anybody have any questions about this slide number 4? I'll take your silence as a no. So moving on to slide 5. This is just a quick intro to mating in assemblies. I'll actually just open up an assembly document as well, just to kind of show you guys the lay of the land as well. And so if you go into new file, make assembly from part/drawing, it'll ask you to save this part. We don't have anything yet. We're just opening an assembly so I can show you where everything is before we kind of jump into everything else. And so I'm just going to save that to my desktop like a fool. And I'm going to label this. Just a sec. I can label this post and you'll see why in a second. Cool. So after we've labeled our blank part file, we will open assembly, select that and press OK. And then you can see now we are in a blank assembly. So we don't need to begin the assembly quite yet because we don't have any parts to put in. But we can now see the other tabs. And so we have assembly now, and that assembly, like we saw in slide 4, has a bunch of different potentially useful tools. The most important being insert components, and that's how you get things into your assembly. And so we have a mates tab, and so mates, like again, I can't open it right now because there's nothing in the assembly, but mates are used for, as you can see in the fun graphic there, mates can add relations between two individual parts in assembly or in an assembly. You can also use mates within drawings in order to, well, add relations between two lines, and that can be seen in slide 6. The specifics of line 5 will be gone over again when we actually have things to put in our assembly. But moving on to slide 6, we can see we can also add mates in drawings, and again, we'll be able to go more in depth with that when we actually start going. I just want to make sure you guys know what everything is before you see it, basically. Does anybody have any questions about that? Great. Okay, so we're going to go back to our post here. So you can just go to Solidworks at the bottom and bring back your post tab. And moving on to slide 7, you can see we have, again, we don't have anything here yet, but we have a materials tab, and the materials tab becomes quite important once we actually have things sketched. But so before we do anything, I'm just gonna, spoiler alert, we are making this first part, this post, out of 6061 T6 aluminum. And so how you find that material is you right-click edit material, or sorry, right-click material not specified. You can then go into edit material, and it will bring up a list of materials you can use from the SolidWorks materials library. So we have a bunch of different options here, and all of these different materials come with a different visual representation in our 3D model, as well as they have their like physical characteristics from lookup tables. And so if I go into aluminum alloys, bring up the drop-down menu and scroll until I find aluminum 6061 T6, in parentheses capital SS, I'm not sure what that's for, but 6061 T6 is the most common grade of aluminum we use in the mech machine shop for manufacturing metal parts, just because it machines really well and it's very strong. And so we are going to apply that material by pressing the apply button. Before we close, however, we can actually add this, we can add aluminum T66 to our favorites by right-clicking and then pressing add to favorites. And so once we're out of here and we right-click 6061 T6, you can see we don't always have to venture into edit material. We can actually, they have a list of favorites right here. And so you can see 6061 T6 is already on there for me. Okay, any questions about the materials? Cool. Moving on to slide 8, we are going to go back to our unit of measurement. So I know this sounds really boring, but these are all important things that we want to configure before we start making anything. And so you can see mine is set to inch, pound, second. Yours may be millimeters, grams, seconds. However, we want to edit our document units and make a custom one. We are going to make a custom unit set because living in Canada, we just can't decide whether we want to follow the metric system or the imperial system. And so you can see I'm going to scroll I'm going to click the custom. And so now it's going to let me edit all of these with little drop down menus when I click them. And so as you can see in the green box there on the slides, inches, millimeters, and degrees is perfect for our basic units. For our mass section, we're actually going to switch pounds to grams. This is because we do most of our sensible scientific calculations in metric, because imperial sucks for science, and so we like to have our mass in grams or kilograms if you're feeling defiant. And then, however, our unit per volume is still inches cubed. Again, you can change this in regardless, or you can change this according to your use case. We just don't really need it for today, so I'm not going to change the per unit volume. And then that is all good for me. So I'm going to press OK. And now you can see we have our custom inch gram second units. All good there? I'm going to assume yes. So now we're going to get into the naming standard. Yay. So every part needs a material, which we already did, and a distinguished name. And so I initially named this post, and I was a fool because a post isn't very descriptive, and it's very hard to find when we're in a large file system with a lot of different parts and a lot of different sub-assemblies that need to go together and have unique stuff, and it's just a whole thing. So what I'm actually going to do is I can actually rename my post in my Solidworks file. This is the best way to rename any parts, because just like refactoring your maybe your code, any relations between a drawing file or a assembly, all those references are going to be maintained when you change the name of your part in Solidworks. If you just go willy-nilly onto your desktop like a crazy person who saves their stuff to a desktop and change the name of the post here, all those relationships are broken, and you're gonna have to go find all of your files manually, which sucks. So take a piece of paper out of my book and rename this using rename tree item. It should give you a new option to name this. And so we're going to name, I believe, do we have it here? Well, this is an injector spacer. So I'm going to, instead of the first two characters indicating the project and rocket number, like you see in slide 9, I'm actually just going to go IS for injector spacer. And so then I'm going to add a part number. So the second two characters indicate the subsystem and then distinguish between a part or an assembly. So the propulsion subsystem is 2, and you'll see those are numbered in our Google Drive if you are a part of that, just like you see on the very right. And as you guys are all honorary propulsion members or real propulsion members, Logan, thanks for coming out. Then we'll the parts we're making for propulsion will be start with a number 2, and because this post is a part and not an assembly, it's going to be 2, 1 in the second two characters, and then finally the last two characters will be the part or assembly index. So within our assembly that this will be in, this is part number 1. So IS-21-01. I know it's kind of hard to see up in the top corner there, but oops. Does that make sense to everybody? So it's IS-21-01, and you can see I just press like rename temporarily. So what we have to do in order to lock in this refactored name is we actually have to Control S save our drawing, and so, or save our part file. So I just Control S, and it'll be like, hey, you need to rename stuff. And so to avoid broken references, you must update where use references and search for documents to update. And so if we click update where use references, because we haven't added this to an assembly or anything yet, you can see there is no references. However, we still need to confirm that we update this regardless if the part has been referenced or not. And so you just press OK, and then everything is going to be fine. You can see on the very bottom, when we get into finding commercial off-the-shelf or COTS components, then we use a Z dash space part number and description. And so you can see we have a 832, an 832 half-inch long socket head cap screw made out of stainless steel. So we have Z and then the McMaster part number. And I'll show you guys what McMaster is a little bit later. The type of screw, the length, and then stainless steel socket head cap screw, just as an acronym there. So does anyone have any questions about that? Again, we'll be able to go through this again once we're actually making our assembly. But if everyone's all good there, I will move on to slide 10. And now we can actually start making stuff. So slide 10, we are making a sketch. So if you go up to the top left corner, get onto the sketch tab and press sketch. It opens up our 3 coordinate planes. And so we're going to make this sketch on the front plane. And so I'm just going to click it here. And you can see, like, just be careful because you can accidentally click multiple, or it can switch to a different plane a bit abruptly. So just make sure you're being very apparent when clicking front plane. And so now we are going to be making a 2D sketch on this plane. And so moving on to the next slide. So we're on step P2 in the top right corner of your slides. We are going to draw a circle. And so a circle is right up here in our sketch tools. As you can see by the little graphic here, you can place a circle by its origin, and then you drag out from that point in order to make it larger. And so thankfully, the size of our circle doesn't immediately matter, and you'll see why in just a second. And so I'm going to use my little pen or pencil cursor here to place the center of the circle on the origin. So now if I move my mouse away, I can change the size of my circle, and then I'll confirm the size by left clicking again. The size of our circle doesn't matter when you initially make it. It just matters that you have a circle at all. Is everybody with me so far? Great. And so now what we're going to do, you can see this blue, this circle is blue. And so that means this line is not fully defined, and we can just change it to whatever value we want just by dragging around. Blue lines are bad because it means things are undefined. And so what we're going to do to define this circle size, we're going to go up right beside sketch or exit sketch. We're going to press smart dimension. And all of these buttons like exit sketch, smart dimension, line, circle, you can all on your own time go into the keyboard shortcuts, and having those to like singular or like multiple key macros makes making sketches really fast. And so I typically set smart dimension to D. And if you want to exit the smart dimension mode, you can also just press escape. If you press escape again, you'll exit your sketch, but you don't want to do that quite yet. But we'll just hop back into smart dimension and click on the edge of our circle, and you can see it lights up orange. And then we have a dimension number there. And so when I place it with the left click, it'll ask me what the actual dimension should be. And you can see it's some stupidly precise number that we don't really care about. And so I'm going to set that to 0.375, so 3/8. And you can see we now have a black line or a black circle, which is exactly what we want. I can click it and try and drag it around. But you can see in the bottom corner here, it says our sketch is fully defined. That is good. And you'll also notice our first ever sketch mate. So it's like checkmate, but a little more fun. The sketch mate here is this symbol. I don't know if it doesn't show a description, but this means coincident. So the center of our circle is coincident with the origin. And so that means they are stuck together, and you cannot drag because there's a relationship coincident, because they're basically stuck together now. So yeah, we've got our 3/8 circle. And so what we can do now is we can, without exiting the sketch, we'll stay in the sketch and we'll go to features, just beside sketch here in the features tab. And then we will click extruded boss / base. And I'm going to left click that. And now it brings us into a new tab, the property manager for our extrude. And so we want to now, basically, this is turning our 2D sketch into a 3D object. Isn't that exciting? What we're going to do is we're going to extrude or set the extrude distance to 6.053. And because it asks for units, but because our base units or our standard units are inches, it'll just auto populate inches unless we specify otherwise. If I put 6.053 millimeters, doesn't go very far. But if I put 6.053 and don't populate the units at all, I either click enter or I click the green check mark. We get a big long tube. Well, it's a post, but you get what I mean. And so there it is. We have our first 3D model. Is everyone with me so far? I'm trying to go nice and slow. You can also tell me to speed up if this is really boring you. But that's all of step P3. Moving on, we're going to add some features to this darn post. And so you'll see in the slides, with step 1 in the red, we are going to select Hole Wizard. So Hole Wizard is right here in the features tab. I'm going to left click Hole Wizard. And now it's going to open up a different property manager for a different feature. And so this is how we make, I'm going to make this a little bigger. I mean, that didn't really help, but hopefully you guys can see that I guess I can move that over there. We have a bunch of different options for hole types. And so we've got a counterbore hole where the head of a screw is recessed beneath the surface, a countersunk screw, or a countersunk hole for a countersink screw. And then we have our regular hole, so that one that would be made with a drill, and then a straight tapped hole. We are making a tapped hole, and a tapped hole is one that has threads cut into it. So internal threads that you can fasten a screw to. And so now that we've selected our hole type, we're going to make sure we are in ANSI inch. ANSI is the, I believe it's like the trade standard for imperial units. And we want a bottoming tapped hole for our type. And then now we'll go into hole specifications. And so we want as you can see in the slides, a 1032. And so that is a type of thread, or it's a screw size and thread combo. So number 1032 just on the side, and we are going to make that a blind hole. A blind hole is one that does not go all the way through an object. And so it's blind because you can't see through it, and blind people can't see. Who knew? And so we're going to make the depth of this blind hole to be 0.6. And remember, we don't have to populate inches. It will do that for us. And we're going to make the depth, I believe that should be fine. It looks like it's getting mad at me over here, but that's okay. The actual depth of the threads, which is controlled by this second blind here, isn't super important. And you'll see why in a second. I guess it's more than a second, but anyways, we're going to finally make sure we check with thread callout in the options. And that just means it'll show this little dotted line when we make the hole, to show that that's not just like a barren hole. It's actually It's actually a threaded one. And so now that we have our hole type selected, we're going to go to the positions tab inside of the hole wizard. And we're not going to click 3D sketch. Do not do that. 3D sketch is complicated and not super useful. What we'll do is we'll actually select a face that will make a sketch on. And so just like we selected the front plane initially, we can just grab this end of our post and click that. And so now you can see we now have the ability to place a hole onto that face. And so I'm just going to use my cursor to make or navigate until I get that coincident on the center of the face with the hole, and then confirm that position with left click. So you can see whenever I'm on this face, it's going to ask me to place a hole. But if you don't want to place a hole, and maybe you need to make some geometry or like placing sketches, excuse me, then you can actually deselect the hole over here, because in the drawing tools, whenever you have a point selected using hole wizard, you'll place a hole, but you can just deselect by clicking that, and you can see now it doesn't, like I can put a line, for instance, if I wanted to. Yay. But we don't want to do that. We actually just need the one hole in this face, and then we can just confirm that. Cool, look at that. That's a hole. And you can see it has our thread call out here. So that's great. And now we are going to move on to step P5, where we're going to use the mirror function on this new feature we've created. So the first, how we're going to, or in order to mirror something, we need to have a mirror plane. And so in order to do that, we go up into reference geometry up here and click plane. And so placing a plane or an axis requires references within your sketch or within your 3D model. And so if I want a mid plane, I can select two different faces, and it will it'll assume on the side here between my references, face 1 and face 2, that it wants a plane right in between them, which is exactly what we want in this case. But you can see there's plenty of other relationships that you can have with your reference plane. However, midplane is the easiest, or is the one that is assumed when you have two parallel. The two parallel faces at a distance away from each other. And so I'm going to select that. And now we have our reference plane 1. So now, is everyone good so far? Everyone's got their reference plane? I hear no objections. So I will continue. And so I'm going to now I'm going to mirror this tapped hole across that plane. And so if I go up to mirror here, you can see in the green, it's going to ask me for a plane, and I will select plane 1, plane 1, and then the features to mirror. So when we're selecting our feature, you can either click this feature directly, like you can see it's selecting 1032 tapped hole, or you can use this drop-down menu here to go to see your design tree, and you can actually select the feature from there as well. And so either way, if you click this or you click this, it will auto-populate the features to mirror section. We're not mirroring any faces, so we're not going to change or add anything to there. And you can see we get a partial preview. You can also change the full preview, and there's like the full hole that will be mirrored across that plane. And then, so once we're satisfied with that, we will click OK. And now we've successfully mirrored our feature. And so that is sometimes easier than making a new one. And we know that our hole here, or sorry, that obviously, I mean, you guys don't know this technically, but I know that if we change the length of one tapped hole, we're probably going to need to change the length of the other tapped hole. So when they are mirrored in this case, it makes it easier because changing one changes both. Thankfully, I did it right the first time, so no worries there. And so I will move on to slide 15. So we're almost done. We're finalizing the post. And so we already selected the material 6061-T6. So that is great. You can see it's very in bold. Every part needs a material, and we already talked about distinguishable name, which we already have. That's very important for mass calculations because it has every material profile has like a density within Solidworks. And so onto step P7 or slide 16. We named it slightly differently than what we have in the slides, but that's okay. And you can see we check mass properties in the evaluate tab, and then ta-da, 28.5 grams. It's slightly more exact in the slides. There's 3 decimal places. My God. And we can actually change that in the options. I would like 3 decimal places, please. And high accuracy. Great. 28.497 grams. Now, does anybody need any time to catch up? You need some time to catch up? Okay, I can wait here and someone can speak or send a message in chat if you or when you guys are ready to go. Also, if you have any questions, feel free to ask.
Can you show the mass properties again?
Yes, sure. So just in the evaluate tab, now that we've selected our
I'm kind of comparing between mine and yours.
Okay. Yeah, so in mass properties, once we have selected our material in evaluate and mass properties, you can see we've got our mass, and it also gives our center of mass from the based on our the center of mass is based on not this point here, but that point is the center of mass, and the center of mass is measured from the origin, which is over there, highlighted in green or in orange on the right side. Yeah, anyone have any other questions?
Yeah, just my units are kind of they just didn't change after I changed them from the custom menu.
Oh, so does it say custom in the bottom right here for you?
It does.
Okay, but then in mass properties, it hadn't changed?
No.
Okay, so
centimeter, cubic meters.
Oh, interesting. So what you might have to do is go into options, and then see document settings should be inches, grams, inches cubed. However, if it's not, you can use custom settings by clicking the custom settings menu, and then changing those manually.
Oh, I see. Well, then if I change them from the like sketch panel, that won't do anything here, right?
It should update with the custom, actually with like the document settings, but if it's not, then you may just have to save your document if you haven't, but I'm not sure why it hasn't updated.
All right. Thank you.
Okay, either way, minor detail. Does anyone, or in terms of the actual modeling, is anyone still catching up? No. Okay, cool. Well, or as far as I can tell. So we will move on to the next part. So we want to make a new part. So what we can do is go into new, just up in the top left corner, select or left click, and then left click on part. Okay. Okay, we're in part number 2 now, slide 17, step M1. You can see file new part. We're going to create another sketch. And so I assume you guys know how to do this now, but we're going to create it on the top plane this time, because, or sorry, no, on the front plane still. That's my bad. We're going to create a sketch on the front plane. We can either select the front plane before and press sketch, or you can press sketch and then click the front plane. And so now we want 2 circles of those 2 diameters. So that'll be, you can just make both circles first without defining their diameters, and then click dimension 2.3, 2.73. Cool. Okay. So now you can see we got 2 circles and they're black. So they are fully defined, which is good. And so now we're going to, just like before, extrude by going into features. We're not exiting the sketch. We're going into features and we're pressing extruded boss/base. And you can see it's auto-populated the filled area, which is exactly what we wanted. So the spot between the 2 circles is what we'll be extruding, and we will extrude that profile 2.375. So you can see there's a bunch of other options in boss extrude. So maybe we want to extrude in a different direction of a different length. That's also a possibility. And there's plenty of options in here, but I'll leave you to explore those on your own. For now, we're just doing a blind extrude up to 0.375. And now we've got a thick circle or a thick ring. Yay. I see a few people are on slide 16 and 17. Just want to make sure you guys are all good to go. No, not good to go. Yes, good to go. You also have you can speak, Logan.
I have to go and turn the mic on.
Oh, geez. I'm so sorry. Either way, if we are, I will proceed slowly just in case you need to catch up. But now we've got our extruded circle. Very good. We should be on slide 19, or sorry, so 18. We have. Okay, yes. So there's a second little note on slide 18. And it's if the regions don't automatically populate when you press extruded boss base, then you just have to select the region between them, and then that should also happen. But then moving on to slide 19, step M3, we're gonna make another sketch. Oh my gosh! So moving into, we're gonna make another sketch on the front plane. You can see it's at the back of our ring here. We're going to press sketch. So now circle, we want another circle. And so what we're going to do is, what I did is to square off my view, I actually just pressed the view orientation button. You can also press the space bar and it should bring you to this view. And then you can rotate around. This is using the middle. If you hold down middle click, or your middle mouse button, you can rotate. I realized I didn't really explain the navigation. And then if you control middle click, you can pan, or you should be able to pan around this way. But the easiest way to get around is the easiest way to square up your part to your face. You can press the space bar and then just click the front view. And so now we want to make a new circle, and we want to make the circle coincident with, or the center of the circle coincident with this inner ring. And so you can see when my cursor is horizontal, that's what that small, I keep almost pointing at my monitor. That's what that small, the small horizontal line is. You can see when our cursor is horizontal to the origin, we can actually place this the center of the circle on the edge of the bigger circle. And so we will just make this whatever size we want. Again, I can oversize it so it's easier to select. And then I'll dimension it to 0.43 inches in diameter. So that's cool stuff. Problem is we can still rotate this around the circle because we're missing a definition, or we're missing a relation that fully defines the center of the circle. And so what we'll actually do is we can left click the center of the circle, and then we can left click the origin while holding control. So that was left click on the center of the circle, and then control left click on the origin. You can see we bring up the properties tab. And so these are those relations I was talking about. These are your sketch mates. And so in this case, we want this point here and this point here to be horizontal relative to each other. And because this point is fixed on the origin, when I add the horizontal relation, you can see that defines our circle. Very exciting. And now I can't flip it around our ring. Okay, is everyone following? Great. And so now we will continue onwards. We have our circle. We're going to exit the sketch. Or sorry, no, we're not going to exit the sketch. That's my bad. We'll do the same thing as we've done before, and we'll just go to extruded boss base. And what we're going to do is, you can see it's kind of like it's actually auto populated this extrude distance using the last length we extruded to. So 0.375 is exactly the same thickness as this as our larger ring here. However, if we want this extruded distance to kind of adapt, if we decide to change the thickness of the overall ring, instead of using a blind end condition where we have to update the extrude length of this circle and the ring separately, what we can do is go into this drop-down menu for the different types of end conditions, and then select up to surface. So you can see now it asks for either the direction of extrusion or the face/plane. And so if you select this top face here of our extrude, so this guy, then you can see it is going to extrude itself all the way up till it's flush with that face. And so now if we change the thickness of our ring extrusion, it will the extrusion of this smaller circle will follow. And you can make sure the merge results here, just below the face, is clicked or is selected, because that will keep these two different extrudes kind of joined as a body. And so when you confirm with the old OK, excuse me, you can see there's no edge between these two now. They have been joined together. Whereas if you boss extruded, you can also edit your features by left clicking here, left clicking on your feature, and then you should get this pop up for your different options. If we edit feature and I didn't press merge result, you can see we get these intersecting faces, which is looks kind of gross and is not really what we want. So I'll change that back to merge. So how's everybody doing? Any comments, questions, hopes, dreams, aspirations, things like that? No hopes? Cool. Me neither. So yeah, I'm just going to square up my face again. I can also, if I'm over here, you probably read in the slides, you can select this, select that face, and then press normal 2 in the pop-up that shows up as well, and that'll do the same thing. All right. So we got our second, we have our second circle. Moving on to slide 20. That was just our merge. That was just our extrude up to surface steps. Sorry, I kind of missed that. And then slide 21 is the radius. So applying a radius to sharp corners is very important. As you can see in the top, or sorry, the rightmost image on the bottom row, sorry, the leftmost image, that is supposed to kind of emphasize what a top-down milling cutter will do when it enters a sharp corner. So for those of you who don't know, here's what an end mill looks like. And so an end mill is this big square drill bit looking thing, which is used in top-down milling. Like you can see, oh wait, no, sorry, there you go. There you go. So these are, this is an end mill. And you can see it's like I said, square, chunky drill bit looking thing. But this cutter is used to do top-down milling, which is how we make a lot of our aluminum parts. So you can see there's plenty of fun examples of what's going on. And you can see that if we look back at the slides, I'll just kind of highlight with my mouse here on this one, a milling cutter that's kind of tracing the 2D profile of our part cannot get into sharp corners like this. And so we never want to design something that is being designed for like top-down milling manufacturing with sharp inside corners, because those physically cannot be made. And so what that means is we're going to use the fillet tool right here, and use the fillet tool and add a radius to that corner. And so how we'll do that is we'll press fillet, another feature in our property manager tab or feature manager tab, and items to fillet. So you can either fillet an edge or a face. If you click face, for instance, you get this gross thing, which is not what we want. It'll just round over every single edge that makes up that face. We want to, we can rotate around using middle click and drag to find these two edges and add a radius. You can see I have the full preview selected in the just underneath the items to fillet, and I've left these two settings also selected, and that just shows me what it's going to look like, and that's good for sizing, like visual sizing purposes. And so I'll select both edges, and you can see we get this nice rounded kind of preview. For those of you who have taken, I believe it's the mechanics of solids. Corners, sharp corners are stress concentrations, which are bad additionally. So, and that's all I have to add on that subject because I've yet to take the course. But yeah, like I said, corners bad because stress, corners bad, or sharp corners bad because end mill. And so we'll make these fillets to be 0.2 inches in radius. And so you can see, unlike all of our complete circles, which were dimensioned to the diameter, any incomplete arcs, so semicircles or like anywhere between a single point and a fully complete circle is going to be dimensioned by the radius. And so just keep that in mind when you are dimensioning stuff. And so, yeah, I just fill in 0.2, press enter for it to update. You can see much bigger, twice as big actually, than our 0.1 inch radius. And then I will select the OK button. And as you can see, it builds up that material. And that is great. Anyone have any questions about that? No, cool. Okay. So now things are coming together. This looks almost like a mid-ring. And so moving on to slide 22, we're gonna make some more holes. So I see a few people are still on slide 21. I'm just gonna use that now because nobody wants to say anything. So all right, we're all on slide 22. Great. I assume we're all following along. We're going to make some more holes using Hole Wizard. So back up at the top, Hole Wizard. We are making a clearance hole this time. A clearance hole is a hole with no threads. It is one that has been drilled out by a drill. And that is this guy here. I keep pointing at my screen for some reason. And so now we're going to dive into types a little bit. And so we're still in ANSI inch. That's the standard we're working in because all of our parts are in inch, are imperial, because that's what the machine shop makes, or that's how the machine shop makes these parts. And in the types, I'm going to select screw clearance. And so different size screws have different size diameters, obviously, and those are nonsensical numbers and also fractions, because thank you, imperial system. Either way, for now, we're just going to kind of nod and say yes and agree with America that everything is correct and freedom is good. And we will ask for the clearance for a number 10 screw. And then you can see you can also specify as the type of clearance. So there's ranges of clearances that will make the fit of the screw, just like sliding through the hole, looser or tighter. And the tighter the clearance on your screw, the harder the less slop there is. But as you may know, not everything has to be super precise in terms of like locating, which is what because this screw isn't really doing any locating. So we actually don't care if there's any slop in that hole. For the screw to move around, all the screw is doing is clamping this mid ring, and you'll see why, and you'll see like what I mean in a couple minutes, not just seconds. And so we're gonna make this a number 10 clearance hole with normal clearance. And then the end condition, we actually just want to go straight through. So we don't have to make a blind, which like we could make a blind hole that goes farther than our 3/8 thick ring, but we can also just select through all in the end condition drop-down menu. And so that is good. Now that we made our hole specifications, I'm just going to square up here. And now I'm going to go and set the position and select this face we're looking at here. And so now we actually want to get this circle this hole in the center of this arc. And so in order to get that easily, what we'll do is we'll actually hover on the edge of that arc. And you can see right here, excuse me, you can see right here in the middle, the center of that arc shows up. And so, and then our cursor, sorry, will then snap to it with the coincident, and we can place it there. And then we don't want to place it anymore, so I'll just press escape to get out of selecting that or holding that hole. And then that looks good. Everything looks good. You can see even the point is now black because it is defined. I can't move it around anymore. And you can see when you try and drag stuff, it gets mad at you and says, cannot drag. It's fixed, which is good. And so now I'm going to press OK, and you can see, egads, we have a hole right through our mid ring, which is good. That's what we want. And so we can move on to slide 23, which is getting into the mirroring, or sorry, not mirroring, but we're going to pattern this now. So we want to make 2 more copies of this in a equally spaced radial pattern. And so how we're going to do that is with the linear pattern up here. You can actually click this drop down menu and find circular pattern. From circular pattern, you can now select features you want to pattern. And so it's a lot easier in this case to select these features from the design tree because we have a bunch of features we need to pattern. So I want to pattern the boss. So this boss extrude, the circle, the fillet, and the hole. So you can see we've defined every part of this feature we want to copy. Basically, like we have the feature in its final state before we copy or before we make any patterns with it. Because if, say, I didn't copy the fillet, then, well, first off, rebuild errors because I don't know what I'm doing. But if I don't copy the fillet, then you'll have to copy it around manually later. And I'll show you after we set this up correctly. But with all three features selected, we can now select the direction up at the top here. And so the direction can actually just basically tells you, or the direction can either be an axis, so whether if you have like a central axis defined for your part, or it can be any circular line or face. And so if you click the line here, you can see it's now patterning around the circle, which is good. That's what we want. But the spacing is all whack. Spacing is whack because we need to change our some of our parameters here to equal spacing, and then you can see equal spacing within 360 degrees, and then we want 3 elements, and so that's just here in the direction section as well. Then we'll move that to 3. So look at that. Now we have 3 partial previews, which is helpful. I can actually make those a full preview and it'll make them 3D, which is fun. But what I was mentioning about not adding all of your features when copying, if I remove this fillet, we can see fillet stays on our original one, but now we'd have to go in and manually fillet every single corner later, which is not super efficient. So we want to try and define everything initially before we copy our features around. And so selecting all 3 features and pressing OK, you can see with very minimal effort, we now have 3 holes in our mid ring. Isn't that awesome? As you can see, everyone's moving faster than I am, which is good. I'm glad you guys are picking up fast. But so is everyone good with 23? Cool. 24. This part is actually done. So in terms of modeling, obviously we want to set the material as aluminum T61 T6. And if you after right clicking this again, if you've added this to your favorites, then it should be in this drop down menu. And then as Logan is so smartly doing, you can just copy the name and then renaming your part. However, we haven't saved this yet. So when we press Control S to save, it'll actually ask us to rename this before we save it from part 2. So I'm just going to do IS now because I'm a little lazy. 21-02. And then this is our mid ring. Great. Okay, that part is done. How are we feeling? Great. Yeah, thank you, Arturo. Okay, moving along. Yeah, we've got everything done here. And so now we are going to make an end ring. And so the end ring is much like the mid ring. However, we have a few different things to do past step M5. So slide 17 through 21. We're going to repeat those steps. And I'm just going to do those. I'm just going to run through those quickly after making a new part. I'm just going to run through this quickly to get back up to speed. Feel free to stop or chat amongst yourselves as we all have fun remaking this thing we just did. But yeah, so I'm just going to go nice and fast. Feel free to stop me if you have any questions. Oops. M5 is there. Okay, sorry. Okay, just let me know when you have gotten to here. So you got your boss extrude circle and then your filleted corners. All right. How we doing? Everyone back to this spot here? Great. Yes, thumbs up in the chat. I feel like a streamer now. Yeah. Right. Oh man, that was pretty pog champ moment, everybody. I guess I gotta get a hot tub now. Anyways, moving on. So step E1, we're making the end rings. And so now that we've made it to this spot here, we're going to do something slightly different, as you probably assumed. So we are going to be making a counterbore hole. And so a counterbore is in the hole wizard. Counterbore is this one here, the first one in the hole type. And we want it centered in the same spot as before. So I can place it before I do any editing. I can place it and then I can go back to type and move things around as well. And so what we want is, once we've placed it, we know where we want it. Now we're gonna change the type. And so you can see this is for a binding head screw, and that's gonna take out literally all the material away from that circle, which is not what we want. And so we want to change the type from binding head screw to socket head cap screw. So SHCS, as you probably saw in the consumer off the shelf. The consumer off the shelf component from before. And so you'll notice in the link in the slides there brings you to a McMaster page. Oops, I canceled out my whole wizard. I will put that back really quick. So I'll just keep that there for a sec, but bring over this. So as you guys probably saw, if you click on this link, it brings you to Trusty Old McMaster Car. And so McMaster Car is a supplier, or yeah, they're they're a supplier company, and they have 3D Solidworks and many other CAD file or CAD program file types to download of all of their parts, basically. This is just one part. As you can see, it's just a single screw, but as you can see, they have a plethora of different things to choose from. And a lot of those components, like your fasteners and your materials, things like switches, transducers, regulators, they got so much crap. They all have CAD files of it. And so it's a super useful resource when designing when designing things that have fasteners and other different components that you will end up buying from either McMaster or another supplier. Excuse me. And so we have selected a 18-8 stainless steel socket head cap screw. It's 1032 thread size, and it is 1/2 inch long. And so you can see this this little image is also accompanied by a 2D PDF drawing. And if we bring that up, you can see they have their parts dimensioned, which is super useful because we want our counter bore to be a larger radius or a larger diameter than the head of the screw in order for the screw head to fit within the counter bore. So we want to make sure that keeping this image in your mind, we want to make sure that the socket head cap screw dimensions line up with the socket head cap screw we are most likely going to use. And so how we know what the dimensions are is back in our SolidWorks, go to show custom sizing. You can actually see, what the different, dimensions are for our counter bore hole. And so we can see, that the bore diameter, we have the through hole diameter, the bore diameter, and the bore depth. All those things we can change within our custom sized counterbore hole. And so we want the fit to be normal, as you can see. And then we're going to make the bore diameter 0.3, we're going to make the bore diameter 0.315. So we're making it 0.315 because, as you'll see, 0.315 inches. You can see that leaves a little bit more space for for material to be. As you may remember, that's only 0.003 of an inch, so 0.003 thousand or so, 0.003 inches. It's larger than the head of our screw, and so pretty snug on the screw head there. And so, but that is, we're doing that so we can maximize the amount of material we have in this section. And then we're going to set the bore depth to 0.2, and that is just so we have a bit more like headroom, literally, between the top of the depth of that bore and the 0.19 inch head of the screw. So they don't have tolerances set up in that drawing, but you want to leave a little bit of room. Like the life isn't perfect, and although SolidWorks makes it seem like that way sometimes, screws aren't going to come back or aren't going to be shipped to you like perfectly on dimension to 1/1000th of an inch, and so leaving a bit of extra room for variance is very important. So yeah, we've changed our custom sizing. The through hole size is fine, and then we'll just make sure that the end condition is through all before saying yes. And so, as you can see, we have a 2-tiered hole now, which will leave space for our socket head cap screw. Yay. How's that for everybody? Good? Great. Okay, so moving on to slide 27. We're just gonna do the same thing. We're gonna circular pattern circular pattern this section now. And so same thing as before, in the drop-down menu of linear pattern, circular pattern. I like to use the design tree to grab my boss extrude, my fillet, and my C bore or counter bore for number 10 socket head cap screw 1. And so now that all of those are selected, we can then select the direction, bop a buoy, and then we're good. Look at that. We have our we have our end ring basically complete. And so this time, we're going to name it injector spacer end ring. And so that is, and we can do that because we haven't saved it yet. We will Control S. Hello, Control S. Save it as is-21-03 end ring or injector spacer end ring, whichever you prefer. And we're also going to make sure to set our material to 6061-T6. And you see the tint did change slightly from the kind of regular Solidworks gray. How's everybody doing with that? Cool. Okay. So I see a few people on slide 26, or one person on 26, 27, and 28. Just want to make sure we're all good to go and proceed. Great. This is honestly better than this is as good as the thumbs up. Okay, great. So now we're going into COTS. We've made it, everybody. We're getting some consumer off the shelf components now. Thank you, Logan, for the hype hands. And so we are going to, we need 6 1032 by 1/2 inch socket head cap screws and 3 1032 by 1.5 inch long threaded rod. And so we're going to download these 3D models from McMaster-Carr. The McMaster-Carr SolidWorks add-in, which you see on the side here, is actually really cool. And you'll see why in a bit, because it actually auto-populates, or if you use any CAD files from McMaster, it auto-populates an order for you. And so not that you'll be making orders to McMaster individually, but that is something you can send off to like your project lead or your subsystem lead for your project, which is super helpful. But yeah, you'll see that in action in a bit. But yeah, so on McMaster-Carr, yoink. Oh geez, this is really bad for, I can't see my tabs when they're up there. This is the same link as you guys saw before. And I'm just going to, oh, everything's big now. If things are big, okay, if things are small, you can go into CAD or see this CAD symbol, and with 3D SolidWorks, press download. Should get it in your browser unless it's forbidden. I'm just gonna press it again and it seems to work fine. And like a madman, I'm tossing it on my desktop. I hope you made a folder. I just didn't want to waste anybody's time. And so we're gonna need multiple of those, but we only need to download one CAD file. And make sure that when you, I'll bring this up here. Make sure you guys rename. You can rename there, because we haven't actually used this in anything, we can rename it on the home screen or while you're saving the file. I don't recommend it if your part is already in an assembly, because then you have to go chasing references. However, we haven't used it yet, so we are free to do Z-part number, and then that is a 1032 by 0.5 inch, and then SS or stainless steel socket head cap screw. Boom. Now this is a lot easier to navigate or to use. And then we also need, as you probably saw in the slides, we need some good old threaded rod, some 1032 by 1.5 inch long threaded rod to be precise. And so I'm going to either from here, you can go into find, or you can go into McMaster or the McMaster main page. We are going to search up 1032 threaded rod. And so we just want 18-8 stainless steel. That's kind of the go-to for fasteners. If there's specific instances where you need a very high strength steel threaded rod, then by all means, you'll pay a lot more money for it. But typically 18-8 stainless is the usual. And so you can see, based on our search, it's actually auto-populated a lot of these filters for us. And so you can see the thread size is 1032, material, stainless, we're in threaded rods, and now we just have to pick a length. And you can see every single length has a specific, or has a unique part number, which we will use to reference it later. And so I'll pick 1.5 or 1.5. And even just from here, don't even have to go into the product detail page. I can just click 3D Solidworks and then download from my browser and slap it on my desktop again, like a madman. Don't shake your head at me, Logan. So now we have all of our cool stuff. Does anyone need any more time on sourcing their materials? That would be this guy. You can see the part number here as well. And this guy. Oh, there's the part number there. But yeah, I'll give you guys just a second to grab everything. Okay, there was links to download those. Cool. I didn't see that in the slides. Anyways, has everybody gotten things? Have we gotten our stuff? The two items on page 30. Okay, I assume we're good because we're on slide 30. And so I'll move on to slide 31, where we're going to hop into our assembly. So we made this already. We made our assembly. And so you just had to open it from our tabs. It should be Assemb 1, and there shouldn't be anything in there right now. So we're in Assemb 1. And what we're going to do is we are going to, if when making the assembly, you saw it prompts us to insert a component, what we'll do now is just we'll press insert up here in the top, and we're gonna select an end ring. And once we select it, you can see it now follows our cursor, and we can just place it wherever we want. So you can see the first thing we've placed is fixed, shown by this in parentheses F here. And so we can't actually move it around our assembly anymore because it's the first thing that was placed in it. However, if you see, the origin of our assembly is over here and our part is over there. So what we're actually going to do is we're going to right click on our part and click float. So we're going to unfix our end ring by pressing float here. And so now we can actually move this around again. But what we're going to do is we're going to actually coordinate the coordinate planes. You can see me highlighting here in the coordinate planes in our assembly with the coordinate planes of our end ring. So you can see I opened up the end ring design tree just using this drop down menu here. And so I'm going to now do some mates. Yay, mates. So we want to mate some things. So I just want to make sure everyone's good to move on to mating. Thank you. I'm going to click mate, the little paperclip right up here. And so now it's going to ask us for our mate selections. And so I'm just going to go into the design tree. And then I'm going to first click the front plane of our assembly 3D space, then the front plane of our end ring. And so you can see it kind of assumes we want a coincident mate. That's exactly what we want. Oh, Chris. It assumes, or it kind of auto assumes we're going to be using the coincident mate, and they're correct. We do want these two planes to be coincident, and so they're just basically moved together. And then we're going to do the same thing on the top plane here, coincident again, very nice. And then finally, right plane and right plane, coincident, and we have fully placed our ring inside of our assembly 3D space. So now you can see if I select the origin, if I show this better, the origin is now in the center of our end ring, which is exactly what we want. How's everybody doing with that? Cool. Okay. So now you can see we don't have the parentheses F beside our first end ring, but we also can't move it because it is fully defined, which is perfect. Okay, so I know you guys have been here for a long time, so thank you for sticking around. I'm going to try and speed up a bit just so we're not here forever. But moving along to the next step, we are going to, oh yes, the slide 32 is just about defining the position as well. And then, yeah, same thing. Will also be, same dealio. That's okay. We've defined our stuff. Now we are moving to assembling. We're going to assemble. And so I'm actually going to, I realized I made this the wrong way. And so that's my bad from what you can see on the slides. And so actually this is a good piece of troubleshooting. So what we can do is we actually want to flip this around. And so if we go into the mates, we're going to select the mate between the front plane of the assembly and the front plane of the end ring. I'm going to right click on coincident and flip this mate alignment. And so it's going to get mad. Boom. It's been flipped. And so it's affected the mates because it's had to, like that flipping also flips the, or it keeps all the mates the same. It was just kind of like, hey, you changed this stuff, but that's okay. And so that, how I did that was I just right clicked and did flip mate alignment between the front plane coincidence. And so now it looks a little bit more like what we're seeing in the slides. And then we're going to add another component. How are we doing, everyone? Cool. So, excuse me, insert components. You can see the open documents here are the ones we've been working on, which is nice and convenient. We're going to grab the post. So you can see it puts the post into our assembly, which is good. We want that. And then we can left click to confirm the position. And so it's still undefined, so we can move it around. But now we have it in here. And so because and you can see it's undefined, or sorry, the position is undefined as well because we have the dash, parentheses dash. We can fix that using the menu and get the parentheses F again, but that's not what we want. We want to define this define its position using mates. And so what we'll do, moving on to page 35, is going to make a lot more sense than initially, or than those plane mates. We're going to make this screw hole and this post concentric, meaning they share a rotational axis. And so I'm going to go into the mates tab again, and I'm going to select this outer face and this inner face. Both are cylinders. It's going to assume we want a concentric mate, which is exactly what we want. One thing to make sure is to lock our rotation because we're assuming in this case that what's keeping us fixed is just the screws. The screws are not going to let us rotate. So we'll just lock our rotation in this assembly. And that just means it won't like rotate along that same axis. But now you can see it's fixed along this. And so now we only need to define its position in one more spot, and that is along this axis. And so how we're going to do that is moving on to slide 36, step A6. We're going to mate the two faces. And so I'm going to select this flat face, and I can use the middle mouse button to rotate around and click that face. And you can see it brings us a nice coincident mate. We'll confirm that. How is that for everyone? Cool. So we're going to do the same thing a few more times until we get what you can see on slide 37. So step A7 there. We want to continue to make some mates by inserting components and then making the mates, and then until we get what you see in step 3, the green with the green arrows. And so that'll mean we have to insert some more components. And again, if you have any questions, feel free to ask while I kind of go through this and just add all of these things. You can also keep the insert components menu open by pressing this little thumbtack. And so I can place a component and it doesn't actually take me out of this menu. I can just pick an end ring again and then boom. So now I have all my components placed in space, and I will define them with some mates. Another way you can do mates, just to get you guys before you start, if you left click and hold control on 2 different faces and let go of control, you can see it brings up this kind of hotbar where you can pick a mate as well. And so I can do the same thing there and lock rotation too. Oh, actually, that's not what I wanted. I didn't want to lock rotation on that guy. Oops. So I will not lock rotation there. Unlock. Okay, cool. So we're going to make these 2 faces, mate those together, confirm that. And then to confirm my rotation of this ring, I'm going to make these 2 holes concentric. And then those will share an axis now too. So you could use component pattern. That's a good point. However, and that's fine for the posts. However, because we have like the middle ring and the end rings are different, it's just easier to kind of put everything in here initially for this first round. But you'll see we will use component pattern soon. Sorry, I guess that was the yes. Okay, I thought I was missing more slot or not chat notifications than that, but I am paying attention. Anyways, concentric, very good. Coincident again. And then thankfully this doesn't take too long until we get to our oops. Nice. Okay. I'm ready to go, but if you guys need more time, just let me know. How's everybody doing? Okay. We're almost done, guys. Don't you worry. Only a couple more slides left. So now that we're here, we've got the a single row of posts, and we've made sure to flip our end ring, so we have a counterbore facing out this way and a counterbore facing out this way. We can see that moving on to slide 38, we're going to add our threaded rod. And so what I'm going to do is, just because it's on my desktop here, you can actually select this, just hold the file and drag it into your assembly as well. That's another way to add to your assembly. I just took it from here and dragged it in, and that'll place it in space as well. And so we're going to do a bit of an advanced mate. So I hope you guys are ready. So I'm first going to make okay, yeah. So first thing we're going to do is we're going to do a width mate. And so in order to get it to a width mate, you go into the mates tab, and then scroll down to the advanced mates tab. Get ready, guys. This is advanced. In advanced mates, you want the width mate. So when we select the width mate, you can see the mate selections now change. And so we're going to select the ends of our threaded rod as the width selections. Oops. And then we're going to select the top and bottom face of our mid ring as the tab selection, or as the tab selection. And then so now you can see we have centered, or we've made the we've centered our threaded rod on our mid ring, which is exciting. And so the threaded rod is what's going to be connecting our two stacked posts together. And then in order to make this concentric, on slide 39, you can either use this first most chamfered thread here, that face, or you can also just pick this circular edge as well, and you can make that concentric with standard mates, concentric with that post. And then you can see if I exit out mates, hide these components, you can see we got stuff going on, and that is good. How was that advanced mate for everybody? Doing okay? I know we've been here for almost 2 hours, but we're almost done. So finally, with our, I'm just going to make these transparent so you guys can see a bit better. Finally, with this mate done, we're going to add the screws onto the ends of this. So we're going to, starting at the top one here, I'm going to do the same thing where I drag my socket head cap screw into my assembly. Again, you can also go to insert components and browse and do the same thing. You can also add them in that way. But so I'm going to be taking my socket head cap screw, and on the same column, I'm going to, I typically like to, you can do this most chamfered thread. You can select this guy, select that circle, or you could even select like one of these circular edges on the top as well. Either way, those are all good candidates for mate, for a concentric mate. With this hole, it can also be concentric with the, this post as well, as you can see. Concentric, and we can make that, oh no, it's gone. And then we can make that actually might be an issue. We can lock that rotation as well. I actually have to hide this now, or change the transparency to see the embedded screw within this post. Then I'm going to make a coincident mate between those two faces, and bada bing, bada boom. You can see there's that 3 thou of clearance between the ends of this screw and that hole. And then we're going to do the same thing on the other side as well. Okay, yes, we're going to do the same thing. So we'll take another screw. Yay. I'm going to rotate it around the x-axis before I place it. And then I will grab this most chamfered face, concentric, Yay. Oh, wow. Almost bang on. And then just make this face and this face coincident. And there I have all of my components installed in a row. Does anyone have any questions about that? No, yes, maybe. Where's everybody at? You can speak up. If you'd like to let me know what's going on. No? Okay, cool. I'll just keep going then. So we have all of our components in a line. Now, Yusuf, like you said, we're going to be using a pattern, but in this case, a circular pattern. On slide 41, we are going to select the circular component pattern in the drop-down menu from the linear component pattern, as you can see. I just want to make sure everybody's following because I see a lot of people all around in the slides. And I'm okay with waiting until you guys are good to go. Okay, Arturo's ready. We're almost done, guys. We're almost there. All right, Karnika is ready. Logan, are you having some issues?
How do you flip this, the part, the second bolt?
Oh, the second bolt. So, because you need to flip it all the way around.
Well,
so what you can do?
Yeah, because it's currently facing.
Yeah, is it facing out this way?
Yeah.
Okay, so what you can do is so you can select your bolt in the design tree here. Go into find the drop down menu and go into mates in SEM1. And then you can see you can select the mate between the coincident mate between those two faces. If you right click that and press flip mate alignment, it should fix itself.
Oh, okay. I see.
Good.
Yeah.
Great.
Okay. Yeah. Thank you.
Okay. How are we doing, Yusuf?
My Solidworks keeps crashing, so I'm just like,
oh no. That's frustrating.
Yeah, I don't know what's wrong with it. So, but like I'm almost at slide 37.
Okay, so I'm gonna forge onwards, just because I don't want to keep you guys any longer than you have to be here. Thankfully, this will be recorded and uploaded to our YouTube channel, and the slides are also always available in the Google Drive. I can also link them in the Skilldev's channel on Slack as well, just so you can for easy reference. But yeah, I'll just keep going, and then we will be done for today. But finally, guys, we've gotten to this point now. We're going to circular pattern these posts and all of our fasteners around this ring. And so if I go into circular component pattern, it first going to ask me what components to pattern. And I'm going to go into my design tree, maybe collapse some of those drop-down menus, and then select my fasteners, my two screws, and my threaded rod, and then my post, and then my other post. Okay, so I've got 5 components I've got 5 components that I'm going to circular pattern. And then the direction of my circular pattern can be the surface of any one of these rings, but I'm just going to pick the first one because that's what the slides do. And you can see, well, it's auto-populated with something, but that's not what we want. We don't want one instance. We actually want, 2 instances. We actually want 3. And you can see our partial preview here looks pretty darn good. See, all of our stuff is in the right place. And when I confirm that, then bada bing, bada boom, we have a completed injector spacer. And so you'll notice two things going on right now. So first, I've got this, or I have two different components that are still left undefined. You can see the dash here for the threaded rod and the dash for this cap screw here. As well as this post. And so I'm assuming what's going on is none of these are, you can see, yeah, none of these are defined in there. None of these have rotation lock, as you can see everything is spinning when I move this, drag this up and down. And so just like I flip the alignments, I'm going to go into each part and find the mates that we have going on here. And then I'm just going to make sure the concentricity between this ring and this post that I made with a right click is locked rotation. And then you're going to do the same, and you can see now it doesn't spin. And I'm going to do the same thing with the threaded rod, mates, concentric, right click, lock rotation. And then, well, would you look at that? We're good to go. Everything is defined, nothing is moving, and I see no more dashes. Woo-wee. Look at us go. And so we'll make sure that we save this as an assembly. And so Control S will save all of the components as well as the assembly itself. SM1, let's call this, well, it's got to be IS following what I've done, or M1 IS if you are following the slides to the T. And then since this is an assembly, it has 0 instead of 2, 1. It's got 2, 0. And then because it is the first assembly, or the main assembly, we give it the designation 0, 0. So it should be M1 or M1 IS or IS -20 -00. And that will be our injector spacer assembly. Cool. And so if you'd like to clean up a little bit, what you can do is you can select your fasteners, these consumer off-the-shelf parts, and you can right click and go add to new folder. And you can rename that COTS. And that just helps differentiate between any, obviously any consumer off-the-shelf components and things that we will have to machine and design and machine ourselves. How's that for everyone? Did we make it? We made it? Great. And so this last slide just kind of highlights the McMaster add-in. If you did download it, then great. But you can see once you have a McMaster account, it actually auto-populates these a order for you based on the parts that are in your assembly, which is pretty cool. So 6 socket head cap screws and 3 stainless steel threaded rods, which is exactly what we need. And then if you press preview order, it actually will send it, gives you prices of the total packs you'll need to buy. So $22, as you can see, and then you can click open order. That'll take you to McMaster and you can place the order. But again, that's more so for your project lead or your team lead to do. But yeah, that's everything. Thank you guys so much for sticking with me for almost 2 hours. We covered a lot, but I hope you guys learned a thing or two. Do you have any questions for me or any comments or any improvements that could be made to this? Actually, before you say that, so it's not on record, I'm going to stop recording.